Alrighty, everyone. So today we are talking about topic 7.9 and 7.10. We are on page 22. Make sure you're following along and taking notes. And just a point of clarity, so last class we covered 7.7, and actually 7.8 is already done. We did it in the very first set of notes. So our very first set was 7.1 through 7.3, and then it also included 7.8. Okay, so we are on to 7.9 and 7.10. This is mostly surrounding Le Chatelier's principle. Okay, see that? Both of these. And what this principle tells us is that we know that these reactions, and really most any system, is trying to reach equilibrium. Equilibrium is more stable, lower in energy, and we as experimenters, as chemists, we can do something to a chemical reaction to throw it out of equilibrium, and then it's going to return. It's going to establish a new equilibrium. And how that process goes is this Le Chatelier's principle. So there's different things that we can do to a chemical reaction that's currently at equilibrium to throw it out of equilibrium. We can change, if it's a gas, like so if we're dealing with any reactions that have gas in them, we can change the volume of the container that they're in, and that has the potential of throwing it out of equilibrium. Aqueous as well, we can do this with, and that's when we add more water to it. So or we could, I guess, boil water off as well. But if we add more water, then that changes the volume that these items are in. Concentration is kind of the same deal, right? That concentrations, if we add more water, that would dilute it. It would lower the concentrations. So we can do things, we can either add or take away items to make concentrations higher or lower, and that would throw off the equilibrium. And then for these endothermic and exothermic reactions, if you change the temperature at which the reaction is occurring, then that throws off the equilibrium as well. So we're going to take a moment to talk about each of these things. Okay, so let's say that I have a chemical reaction here. So I have this chemical reaction of N2 plus 3H2 is going to result in 2NH3. Okay, and we've done this before, and I'm going to put it over here in the notes here. So we have 1 mole of N2 gas plus 3 moles of H2 gas, and that's going to result in 2 moles of NH3 gas. And we talked about this in class today, that currently on the reactant side, do you see how we have in total 4 moles of gas? And on the product side, we only have 2 moles of a gas. So then what if, as a chemist, I took this reaction that was at equilibrium, and then I have it in this container that has a piston, and I push down on that piston, so I am reducing the volume. Okay. When I reduce that volume, that space that the gas is in, the pressures increase. So the stress is actually an increase in pressure. And so whenever you add a stress, whether it's increasing the pressure, concentrations, temperatures, the reaction responds to that stress by doing exactly the opposite from that. If I make the pressure higher, then the reaction isn't going to do something that's going to make the pressure even higher than that. It's going to do something to make the pressure lower to get back to where it was before. And so what would it do then? If I decrease the volume, which makes the pressure increase, what reaction is going to be favored? Is it going to be the forward reaction, or is it going to be the reverse reaction? Well, in this scenario, if we favor the forward reaction, this would lead to a decrease in pressure. And the reason why we have a decrease in pressure is because 4 moles of a gas would be turning into 2 moles of a gas. And so as a response to this stress of lowering the volume, making the pressure higher, the forward reaction will be favored. And the reason why is because 4 moles of gas turns into 2 moles of gas, and that will lower the overall pressure in the container. Okay, we're on to the next page, page 23. Same idea here, that if I have a container and I do the opposite, I raise that piston, so that would make the volume bigger, that actually decreases the pressure. And so if the pressure decreases, then the reaction is going to favor the direction that increases the pressure, that has more moles of gas than it does on the other side. They may ask you about Q and K on this, so let's think about that for a minute. If we know that we are going to favor the reverse reaction, okay? So if we are favoring the reverse reaction on this, and it was thrown out of equilibrium, so Q was here, it was with K, and then what we did is we raised the piston, and that's going to decrease the pressure, and then the reaction responds by favoring the reverse, so it can increase the pressure, more moles of gas. Then what did that mean? Did Q, when I did that, did Q increase or decrease? And so I'd say, well, then it would have resulted in a higher Q value, that it was here, and then I threw it out of equilibrium, and now it's going to favor that reverse to get back to equilibrium. All right. What about concentration changes? So I'm going to have the same reaction. I'm going to rewrite this for us. So I have N2 gas plus 3H2 gas results in 2NH3 gas. Okay, so how I've always done this is up above a reaction. This is where I indicate the stress. Okay, this is where I show what me as a chemist, what I'm doing to this reaction. Below the reaction is where I'm going to address how the reaction responds. How does the reaction respond to the stress? So the stress is adding more NH3. So I'm going to increase my NH3. Reminder, the reaction's response to this stress is always doing the exact opposite of what the stress is. So if I add more NH3 in there, the reaction is going to then respond by decreasing the amount of NH3. Well, NH3 is a product, and how we decrease a product is by favoring that reverse reaction, okay? That we have products turning into those reactants, and so that would decrease the product, and that would increase my reactant. We can ask all kinds of questions like this. So an example, if in a question it says, okay, we're going to increase the amount of NH3, I could ask you, will we favor the forward reaction or the reverse reaction to get back to equilibrium? And in this scenario, we'd say, I'm going to favor the reverse. I could also ask you about the amount of N2 or the amount of H2. I could say, is the amount of N2 and or H2 going to increase or decrease? And you could say that it's going to increase. Another thing I could ask you would be about the Q value, that how is Q was equal to K, but then I added this stress. And so then what happened to Q? Well, that means that Q increased because now it's going to try to get back to where K is because I'm favoring the reverse reaction. We can also like mathematically think through that. QC, that would mean concentration of NH3 raised to the second, concentration of N2, and concentration of H2 raised to the third. And what did we do? We increased this item right here. We added to that. And so that would make the Q value bigger, right? This increases Q. And so then it tries to get back to equilibrium by favoring the reverse reaction. Okay, same idea, but now I'm going to be removing some NH3. So reminder, how I do this is the stress, what me as the chemist is doing to throw this out of equilibrium is going on the top of the reaction. The response is going down below. So I'm going to decrease the amount of NH3. As a response to that stress, the reaction does the opposite. It tries to increase, and it does. It increases the amount of NH3. Well, NH3 is a product. And so in order to make more of this product, the reaction is going to favor the forward reaction. That means reactants are going to decrease in order for this product to increase. Okay. Again, we could also say that Q, as a result of the stress, is now lower than K because we're going to favor the forward reaction to get back to K. Cool. Now, what if we dilute, okay? Meaning that I have, this reaction is happening, okay? And these are all aqueous. So I have 1 mole of aqueous items on the reactant side, and then in total, I have 2 moles of aqueous on the product side. I really, really like to think of this stress very similar to the gas when I was increasing or decreasing the volume on the gas. Think of it like the piston. It's like the piston is down here, and then I raise it up there, okay? So I'm adding more water in there. That would dilute it. That would cause the stress being like overall that there would be a lower concentration, right? Less stuff. And so then the reaction responds by making more stuff. It wants to fill that space. And so if we have 1 mole of an aqueous item and then 2 moles of an aqueous item, the reaction will favor this forward reaction because then 1 mole turns into 2 moles. It fills up that empty space, right? It would increase the overall concentration that we'd have over here. Okay? So just like the gases and the piston, I'm going to take this piston, I'm going to raise it up, and that decreases the pressure in there. In this case, it's not pressure, it's like the aqueous, it decreases the concentration. And in order to fill that space back up, in order to increase the overall concentration of items in here, it favors the direction that has more items. 2 moles of aqueous versus 1 mole of aqueous. A lot that we could say, just like before, we could say that we're going to favor the forward. Oh, another way that we say this is the equilibrium is going to shift to the right. Like these are synonymous, by the way, like favoring the forward or shifting the equilibrium to the right, versus if it was favoring the reverse, it would be shifting the equilibrium to the left. And we could also say that when we did this, when we added the water in there, that caused the Q value to become lower than the K value because it's going to favor the forward to get back there. Okay. The last one that we were talking about, because I'm trying to remember, I'll look at the pH on this one, is temperature. So when it comes to temperature, it really depends on if a reaction is endothermic or if it's exothermic. Okay? So this N2 plus 3H2 results in 2NH3. The way this is written, I can tell that it's exothermic, okay? That its delta H is some negative number. And the reason why I know that is because they added heat on the product side. If it was endothermic, if delta H was a positive number, then heat would have gone on the reactant side. All right, great. Now, if something is exothermic with this negative delta H and our heat is on the product side, I'm going to rewrite this down below. N2 plus 3H2 results in 2NH3 and then heat. Okay, just like before, the stress is what I'm going to draw up above. The response is what goes down below. So what if I have this reaction and it's in equilibrium, and then I'm going to increase the temperature? So me, the chemist, I'm going to add the stress of increasing the temperature. I'm going to make this higher than it wants to be. Okay? As a reaction, it's going to respond to that by doing the exact opposite. It's going to try to decrease the temperature. It's going to try to decrease heat. How can it decrease heat if heat's on the product side over here? Well, we can do that by favoring the reverse reaction. In a reverse reaction, products turn into reactants. That we can get the products to decrease and the reactants to increase, one of those products being heat. Heat will be consumed in this reverse reaction here. So when temperature increases and it's an exothermic reaction, the reaction responds by trying to decrease the temperature through favoring a reverse reaction. The opposite would be true if it was an endothermic reaction. I have an example of that. Yeah, let's look at this one. Okay, page 25. This is supposed to be a triangle. This is supposed to be a delta H. So a system represented by a chemical reaction equation below is in a state of equilibrium at 25 degrees Celsius. Describe the color change that would occur if the temperature of the system increased to 75 degrees Celsius. All right, I want to rewrite this. So N2O4 results in 2NO2. The delta H on this guy is positive. It's a positive 57 kilojoules. So that would mean it's endothermic. So I think of heat as a reactant, that it's consumed in this reaction, at least when the forward reaction is happening. Now, just like before, the stress, I'm going to write that one up above, and the response I'm going to put down below. So the stress, what I, as the chemist, am going to do is I took this reaction, it was at 25 degrees, and I increased the temperature to 75 degrees. Like, I am adding heat. So the reaction responds by trying to decrease the amount of heat. Well, how do we decrease a reactant? We decrease a reactant by favoring the forward reaction, in which reactants turn into products. So that would mean that our reactants are going to decrease and our products are going to increase. So we are going to decrease the colorless thing, and we're going to increase the colored, the brown item, okay? When this stress occurs. So describe the color change that would occur. Well, with this stress, the color change that would occur would be that it would become a darker brown color. We would increase in the brown color. Okay, nice. All right, just a reminder with pH. First off, the name of H3O plus is hydronium. Hydronium is just an H plus and a water molecule. So like H plus a neutral water molecule actually gives us hydronium, H3O plus. So we'll learn more about this when we dive into our acid and base unit. Man, that's coming up quick. It is absolutely acceptable to replace hydronium with H plus. We're just saying, yeah, we know that these H plus, that they're in water, that like they're reacting with water. Okay. So if we increase the amount of H plus, that makes it more acidic. If we decrease the amount of H plus, that makes it less acidic, more basic. And then pH ties to this. The stronger the acid, the lower the pH. And then the weaker the acid, the higher the pH. Let me say that again in a different way. The stronger the base, the higher the pH. The weaker the base, the lower the pH. Okay. A system represented by a chemical equation below is in a state of equilibrium at 5 degrees Celsius. If the temperature of the system increases to 99 degrees Celsius, will the pH increase, decrease, or remain the same? This again was supposed to be a triangle. It's a delta H. And our delta H here is positive, so that means this is an endothermic reaction. So I'm going to write heat over here as a reactant. And like I've been doing, I'm going to write the stress, like what me as a chemist, what I'm doing to this reaction to throw it out at equilibrium. That's going to go up above, and the response is what's going to go down below. So I increase the temperature. I go from 5 degrees Celsius, and I put this on a hot plate, and I increase it till 99 degrees Celsius. So that means the stress is an increase in the heat, and the reaction responds by decreasing heat. Okay, great. Now, if we want to decrease heat, and heat is a reactant, that means that we need to favor the forward reaction. We need reactants turning into products, because that would decrease reactants, and that would make products. Well, what is one of these products? Hydronium, H3O plus. And it turns out that if we add this stress, the result is an increase. The reaction is going to increase the amount of H3O plus. What did we say up above? If we increase the amount of H3O plus, it becomes more acidic, which decreases, let's write the whole thing, more acidic, which decreases the pH. Alrighty, nice. Okay, we're gonna save this part really quick. And so this is another example where temperature changes. And then find the initial partial pressures of the gas. A chemist mix 80% of N2 and 20% of O2 by mole in a vacuum and finds that the total pressure is 1. Okay, and then find the equilibrium partial pressures at 25 degrees Celsius, and then if the temperature increases. Did they ever tell us that this one's endothermic or exothermic? No, okay, I think I must have missed that. But is this the same as another one? Okay, so we would need, for this last part here, I would need to know if it's endothermic or exothermic. Delta H. It does give me a new KP though, so that could tell me if the temperature increases to that temperature, find the new equilibrium concentrations. And when they give me the KP, yeah, we should be able to do that. Okay, This one will be a great exercise for us to start with at the beginning of next class. I could definitely see a question like this showing up on the free response. Percentages and total pressures. So you can think about that. If it's 80% N2 and 20% O2, and then the total pressure is 1 atmosphere, then what is the partial pressures of each of those? And then find the equilibrium partial pressures, find the initial partial pressures, and then find the equilibrium ones, yeah. So then we'll probably use an ice table. Yeah, we'll use an ice table for part B. So let's write that little reminder for us. And then after we have our ice table, then we're actually going to use a K expression, so that'll be cool to figure out the concentrations of these items at that new equilibrium amount. Okay, nice. Yeah, that'll be a great one to start with. Everyone, thank you so much for your hard work, and then I will see you all in class on Friday.